What we're going to do today, I'm going to introduce the course, a few things about how I intend to teach, and useful for you to know. And we talk about what I'm going to cover and why it's important, why I think it's important anyway. And then we'll kind of jump right into the internet. And by the time you leave the class today, you should have some sense of what the internet topology looks like. What does the internet look like at a high level? And so anyway, that's what we're going to cover in the class today. So let me just get right into it. Let me start with who I am. So my name is Keshav. I'm going to be the professor teaching the course. Andy Curtis, who's sitting in the corner. Andy, maybe you should stand up. Andy is my PhD student, and he's graduating this term. He's going to be a professor soon, I hope, or he hopes anyway. And so Andy's going to be doing some of the lectures. So we're sort of co-teaching the course, though I'll be doing most of the lectures. Andy will be teaching two specific sections, one on data centers, which is what his expertise is in, and one on transport layer protocols. And that will be later on, and you'll see more about that. So I've been doing networking for the last 20, let's see, I can add one more year now, 24 years. So probably since before you were born. So I know more about this stuff than I want to, and need to probably. And unfortunately, that means that I'm approaching this course from sort of the wrong angle. Okay, most of you probably don't know much about networking. That's why I'm taking the course. And what I'm going to try and do is to try and put myself in your shoes, so that I didn't know what would I want to know if I didn't know much about networking. So I'll try and do that. I don't know how effective that will be. Okay, let me try and explain a little bit why this is an unusual course. And the reason is because computer networking actually is a sort of a specialized topic, or has been viewed as a specialized topic. And it's rather unusual that we are presenting it for non-majors. And the reason why we're doing it is because it's a very important topic. And in about 5 minutes, I'll explain to you why it's very important. It's important in many, many different ways. But the second part of it that is important from your perspective is that each of you hopefully will be able to take from this course something that you can use in your life and in the work that you do. So if you do GIS, if you do pure math, if you do whatever, you can actually take something away from this course and make it part of what you do. That's my hope. And so the course will not be going into as much depth as it is into breadth. So, okay, the idea would be to cover many topics that are shallow, right, rather than going into one topic very deep. Okay, each of the things I'm going to touch upon in the course, you can go very deep into. Okay? You can spend years studying it. In fact, just as one thing on topology and protocols and services, I could do a whole course on topology just on that alone. But we won't. So it's more like a survey, kind of looking over a very large landscape and kind of going through it. So it's like traveling through a country, right? You could go on a train, or you could fly over it, or you could walk through it. If you walk through it, you see a lot more, but it takes a very long time. So here we are going to be, flying, not in a jet plane, but in a paraglider. So it's kind of moving fast, but not too fast. And you'll see something of the whole thing. Okay, so I like to run courses in a particular way, and I'll explain what that is in just a minute. And the purpose of the way I run the course is because I want you to be engaged with the material, okay, and I want you to be paying attention. And there's a lot of material, and if you don't pay attention, you'll lose it, right? Okay, so now to a very important chart. This is what the chart looks like. This is the x-axis, and x-axis is time, and the y-axis is human attention. And this is like 1, which means highly attentive, and this is 0, which is like catatonic, vegetative state. And it goes something like this. And this value, anyway, below this, the threshold value t, let me see, capital T maybe, you basically aren't even alive, you can't remember anything. And that's about 20 minutes for most people. Okay. So what this says is that when you start the lecture, you're kind of paying attention. And then you zoom down at 20 minutes, you know, I could be poking you with needles and you wouldn't respond, okay? Now, how do most people teach? In the first 10 minutes of class, 5 minutes of class, when you have the peak attention and doing random stuff like telling you when the exam is, what the class is about, and random stuff like that, all the administrative stuff. And you know, by the time all the really important stuff is happening, you guys are sleeping. Okay? So I'm not going to do that. Instead, what I'm going to do, oh, I forgot, there's actually there's a dotted line over here, and then there's this other thing, and this is end, and this is end minus 10. So 10 minutes before the end, you sort of say, oh man, it's going to end. I can't believe you guys pay tuition for this kind of stuff. But at any rate, 10 minutes before the end, you wake up and say, oh, it's going to end, this is going to be over, life is great, and you wake up. So the way you capitalize on this human attention curve is like this. What I'm going to do is I'm going to teach 20 minutes, the first 20 minutes, and after 20 minutes, when you're just about over here, I'll do the first break, which is a 5-minute break, or I'll say approximately 5-minute break. And I'll tell you what I do in that break in a moment, and then there'll be another 20 minutes, and then another approximately 5-minute break, and then there's a 30 minutes at the end. And the 30 minutes at the end is actually 20 plus this last 10. So your actual attention is going to look like this. It's going to go down and up and then down and then up and then, wait a minute, yeah. All right, let's see. So there's this recovery period which takes 5 minutes over here. So we kind of unknown state over there. You go up there and then you have another recovery period and then it goes down and it goes up again, right? Because it's towards the end. So there you go. So you're always above the threshold value t. You're never going to be below threshold. So that's the new and improved curve, which means that if you come to class a few minutes late, you're going to miss all this good stuff right here. So you know, so you shouldn't, okay? So you shouldn't do that. And so that's the way I'm going to run the class. And I've been doing this for years, and most students like it. Okay, all right. Okay, so the other thing I do here, I use the chalkboard. Okay, I don't use, there'll be no PowerPoint and no whatever, anything else. It's just going to be chalkboard. I have high-tech equipment though. I think I brought it with me. I have a high-tech, I have something really special here, which is I have colored chalk. So this is, so I have kept up with the times. It's state of the art. I have even 3 different colors: orange, green, and blue. So it's pretty cool. Okay, it's surprising how useful it is. Okay, right. Okay, so there is something else, the high-tech part, which is something called Piazza. And if you go to piazza.com and you look for Waterloo and CS436, you'll see that there is a course set up already. I did it a couple of weeks ago. And you can create an account for yourself on that. So Piazza is a question answering system. It's kind of new. It's a startup out of Stanford. It came out, they've been using it at Stanford for the last year or so, and they've been using it at various other places. Waterloo is one of the first universities in the world to use it. And I used it last term for another course I was teaching. It's really nice. You can ask questions either using your actual name or you can ask anonymously. And any question you ask is kind of immediately updated on the site, and then people can answer, or I can answer, okay, or Andy can answer within a few minutes. And so it provides a way to ask questions and get answers quickly from your classmates and from the instructors. It also allows me to post announcements, things like that, and to have it available to you right away. And so it turns out to be really extremely useful. So I'll be using this. I don't plan to use the Desire to Learn system, okay, which is the sort of, this is also an official, it's also approved at the university, but it's much easier to use, much easier to learn, etc. And so that's what we'll be using. So that's the high-tech part of the course, I guess. So that's what we're going to do. Okay. Okay, then the last part I wanted to talk about in terms of course operations is the marks distribution. Right, I forgot to mention what the second part is. So the first part I do this roll call, the second part over here in the second 5 minutes. So I have a bunch of stories I tell students, okay? And these are kind of stories with a moral or at least something you learn. And so people usually forget the course material, but they remember the stories. So I'll tell you the stories. I enjoy telling them. And they all have something you can learn from. So anyway, I'll do, and then when I run out of stories, I'll juggle because it keeps you awake. You know? So the second, this break is just meant to wake you up. Okay, so I'll do whatever it takes to wake you up. And by the end of this course, you should be able to juggle 3 balls if you've been paying attention. Okay. Okay, so come back to the marks distribution. We're going to do something a bit unusual. So let me tell you the normal stuff. So there's 20 for a midterm. Piazza, if you go to Piazza and sign up, the first announcement is a 6-page course handout, which has everything I'm saying pretty much, plus all the details of what's going to be in every lecture and stuff like that. So you can look it up. But anyway, 20 for the midterm. There's 20 for the final. Both are open book and open notes, so you don't need to memorize anything. And then there's going to be 20 for 20 homework assignments. So there will be 20 homework, actually there'll be more than 20 homework assignments. We'll take the best 20. Okay, and I'll explain what that is in just a minute. And then there's going to be 3 projects. So project 1 is 10, project 2 is 15, and project 3 is 15. Okay, so let me explain what the homework assignments are. The homework assignments are based on this theory. Actually, it's been found, it's not just a theory, it's something that actually seems to work, that you learn best when you kind of know what you don't know. Okay, so when you're trying to read, you're reading something and somebody's saying read to understand something, okay, as opposed to just read something, there's a difference, right? So the way it works is like this. On Piazza, what will happen is that we'll be posting some simple questions, okay? Nothing complicated, really pretty straightforward, that you should read before class, okay? We're not expecting you to answer it before class, but read it before class, okay? And there'll be kind of straightforward questions, and the answers are going to be so short that you can write them on an index card, okay? All right, so on both sides of the index card is all you need to write the answers on. And in the next class, you turn in your index card, okay? And each of these is worth 1 mark, that's it, okay? And you're pretty much supposed to get that 1 mark, okay? If all you have to do is show up in class and pay attention, you should be able to do it. It's not something very complicated. So these 20 marks for homework assignments are essentially kind of a freebie, okay? But you do have to come to class and pay attention. And so I have 2 daughters, and I managed to convince them to make bundles of 21 index cards each. And there's 42 bundles, so you guys can help yourself. Just take one and pass it along. And so this way, all the index cards are the same size. Yeah, so you just take, pass the bag along. Yeah, there you go. And so you don't need to go and get index cards. The last time I taught, I had people get index cards, and every one was a different shape and size, and it was a pain in the neck to grade it. So this way it's easy. So we'll just grade it and give you the mark, or a fraction of a mark if necessary. And that's the 20 homework assignments, okay? But the purpose is very clearly to help you know what you don't know, so that you're paying attention in class as to these are the 2 things or the 3 things that I want to learn, and that's going to be helpful. So I did this last term. Last term I had 32 homework assignments, and the students said it really helped get them. They really understood what was happening because you would come to class and they'd kind of know what to expect. Okay. All right, so that's the homework assignments. There's going to be 3 projects, 10, 15. Each project is sort of think of it as a take-home or homework assignment kind of thing. and each will last about a month, okay? And I'll explain what those are in just a moment. So these two involve programming, and this one does not. The first one does not. The first homework assignment or project is going to be giving you a sense of what the internet is, okay, by doing something about it. So what you'll do in that homework assignment is to actually use your home or course account to study the internet. And it turns out there are about 10 or so different tools that you can use that allow you to learn a lot about the internet. You can actually find quite a bit of stuff just by using these tools. So all the tools are open, free and open source, so you can, I'll tell you what the names are, and you'll actually be able to find out a lot about the internet by using those tools. So that's the first assignment. In the second assignment and the third assignment, they both, actually the second and third are related to each other. The second assignment is going to be writing a piece of software that becomes part of the internet, okay, that becomes a service on the internet. So for example, you might be writing a web client or a web server or a mail server or a mail client or something like that. So this will be essentially implementing something called protocols. I'll explain what those are. And what you'll end up doing is actually having something running that's part of the internet itself, so other people can use it. So it should be an interesting thing. The amount of programming you need to do is not a lot, and we'll give you some sort of sample code and so on. But you will need to do some programming, and I assume all of you have taken 250 or equivalent, which is the prerequisite for this course. So you should have some familiarity with programming. Okay. I think that's all I wanted to say about course. Are there any questions about course operations at all? Anything? So this is all sort of the basic stuff about the course. Any questions from anybody? Okay. All right. So let's move along then. I'm going to show you a very important picture. Okay. Right. So how many of you have studied Plato or the Republic? Good, I'm glad. Oh, you have? Okay. You're starting to read it. Okay, then you should keep quiet. Okay, this is from Plato. All right. So this is a very important figure. So what is that? Sorry? Somebody's triangle. Why is it a triangle? No. I didn't say anything. I asked you what it is. You said it's a triangle. I didn't say. So what's a triangle? A three-sided figure. What's a side? What's a side?
Collection points.
Collection points. There will be straight line, straight?
Collection points.
In straight line. Is that straight? It's not the least bit straight. In fact, that overlaps over there. See, looks more like a TP than a triangle to me. It's not a straight line, right? It's not the least bit straight. Okay, but yet you said it was a triangle. So why?
Perspective.
From your perspective. Huh?
Faculty of Math. You usually call that.
Okay, we're getting somewhere now. So he's from the Faculty of Math, and when people draw these sloppy figures on chalkboards, they think it's a triangle, right? Now let's focus on this right here. So you said that reminded you of a straight line, even though it's not straight, right? So what is a straight line anyway? Anybody want to answer that? Can we have straight lines? Yes? Yeah? Right, I understand. Shortest distance between 2 points on an appropriate geodesic in space-time. Got it. But, can we have it in real life? A straight line. I mean, if I draw a line, any line, can it be straight?
No.
Not perfectly, right? If I draw even the most straightest line, atomically it's bumpy, right? At the level of atoms and molecules, it's bumpy. So actually, straight lines don't exist, right? Straight lines don't exist in real life. So triangles don't exist either. It's something you learn today, right? Every day you learn something new. Triangles don't exist, neither do rectangles. Actually, circles don't exist either. All geometric shapes are non-existent. In fact, they only exist in one place. They exist only in your brain, not in the real world. So triangles and straight lines are actually mental constructs, not physical constructs. They don't exist. Okay? They don't really exist at all. So why is this important? Okay? What's important is that when you were born, presumably you didn't know what a triangle was. Okay? You didn't know what a straight line was. Yet, at this point, you at least know what a straight line is in your head, right? So the concept of triangle, which existed in somebody else's brain, got into your brain, right? So you changed your brain. No, I mean seriously, I'm not making this up, right? So your brain was actually changed. In what way? What way is that now there's a part of your brain, okay, some neurons, which have the concept triangle inside them, which represent the concept triangle, which wasn't there before, right? So now if I draw this sloppy thing like this, really sloppy, you know, it's not even three lines, it's like one curved line, one straight line, your brain still says triangle, okay? So somebody did a pretty good job of brainwashing you, in the good sense, right? Now, the purpose of education is to reformat your brains. Like you reformat a hard drive, I want to reformat your brains. Okay. How do I do that? Okay, I come here and I draw all this random stuff on chalkboards, and so that's supposed to change the neurons in your brain. That sounds crazy. You know, how can you do that? You know, it's like somebody saying, "The way I'm going to teach you to drive a car is I'm going to, you know, I don't know, show you some pictures, and then you know how to drive a car." Right? What's missing? What's missing is that I can't change your brain. Only you can. Okay. The only way that we know, after thousands of years of effort, to change anybody's brain is to show them stuff and have them work at it. Okay. And when you see enough examples of triangles, you know, somebody draws this and says that's a triangle, or that's a triangle, and this is a triangle too, etc. At some point you make this concept, yeah, straight line, that's a sort of a straight line, that's sort of three sides, that's sort of a triangle. You have to make that effort. And when you make that effort, it gets into your brain. And that's what happens with education, okay? And that's what's going to happen in this course, is that I can talk till I'm blue in the face about protocols and services and networks and routers and hubs and this and that and the other, but until you make the effort, okay, instead of playing with your fountain pen or whatever it is, you will not understand what I'm talking about. You'll not understand what I'm talking about unless you make the effort to take what's on the board, think about it, and internalize it, okay? And that's why there's an example. So Plato actually, in my opinion, was wrong. So Plato said, Plato said that this actually, Socrates was supposed to have drawn this on a sand, and some nobleman came, and this exact same dialogue happened. And what is this? And the guy said, it's a triangle. Why is it a triangle? The whole thing. Plato's conclusion was that these shapes, or ideas as he calls them, are eternal and actually are in your brain, okay? And you already know everything from the time that you were born. You already know the concept of a straight line, etc. I don't think so. I don't think he was correct. What I think is that by mental effort, you can actually change your brain, okay? And that's the point of education. If you couldn't change your brain, why bother going to college? Why bother going to school? If you can't change your brain, if you're going to be at the same level as a high school student, why bother? So effort is required. So my part of the bargain is I'll explain things as many times as is necessary to make it clear. And your part of the bargain, to help yourself, is to make the effort, to kind of do what's necessary to internalize it, okay? And that's how you're going to learn. And I actually know all this stuff already. Otherwise, I wouldn't be teaching you. So this is all this is for your benefit, right? if this is a course for me to learn, I wouldn't be doing this. So this is for you anyway. So that's the need for effort. Okay. Any questions about that? Okay. So I don't know if you got to this part yet, but it's in book 5, so you can read the introduction to the first part of book 5 is this one. Okay. So for doing this course, you're supposed to know a little bit about systems and a little bit of programming, and hopefully you know both. We don't have any requirement for knowing a particular programming language. You know, you don't need to know C or C++ or Java or whatever. If you feel comfortable programming in Perl or Python or whatever, that's fine. You can do that. And you need to know a little bit about systems, but if you've taken CS 250, which I think is a prerequisite, you should be in good shape. All right, so that's sort of all I'm going to do about this part here. And I'm going to go into sort of what's the course about, and everything about here is sort of general. Okay, any questions so far about this? Okay, so I want to set the stage for what you learn in the material and the importance of the material by just taking you back a few years, let's say perhaps to the time just before you were born, okay, which would be, I guess, in the early 80s. And that was before the internet was widely used. Actually, before 95, it wasn't really widely used at all. In those days, if you wanted to correspond to somebody, that usually meant writing them a letter. Okay? If you wanted to do some research in the library, looking up a fact, looking up something, that means you had to go to the library physically, and you look at the card catalog, and you'd actually have to do that. You had, for most people, no email, no cell phones, no Google, no websites, okay, and access to information was limited. So if you lived in a part of the world which didn't have access to libraries, you had no books or that you could read. When I was undergrad, I did my undergrad studies in India. We had no textbooks that we could buy. So we would, the instructor would buy a book, and we would go and photocopy it. Luckily, copyright laws were not enforced in India at that time. And he would just photocopy the book, and we would each get a photocopy of the book, and because we couldn't get the books. If you wanted to write programming, if you wanted to write programs for implementing a particular protocol or something, or write software, all the standards were in libraries because it wasn't available on the network, so you couldn't teach anybody. So it was this very segregated, partitioned world. Today, you can imagine that somebody is in Tahrir Square in Cairo. They take out their cell phone, they take a video, they post it on YouTube, and then they send a note on Twitter saying, here's my link to what happened. Okay, just yesterday on the radio, I heard the story where some official, I forget which country it was, said, oh, I never said this, I never said it, but somebody said, no, somebody videotaped it, put it on YouTube, and here you said this, right here, right? So we see this happening all the time, with the presidential campaign in the US, you'll see there'll be people who are actually going their cell phones, tracking candidates, stalking them almost, and putting up images and videos so that citizens are able to actually publish videos, text, blogs, whatever, and have the whole world listen. So if you think about it, from the time since Gutenberg, the ability to publish has been controlled by a few people. Okay, the publishers and editors, TV journalists, radio broadcasters, and people like that controlled the ability to access ideas. Okay, if you look at North Korea, that is still the case today, right? The North Korean government controls all mass media. Because of this, if something happens, there's no way for anybody to know what happened, right? If there's a chemical spill or something, nobody knows about it because it's a clampdown, don't talk about it. And this was happening in Soviet Russia, it happened in the, sort of behind the Iron Curtain. It happens today in North Korea, continues to happen today in North Korea and Myanmar, places like that. Would that happen today here? Let's say there's a chemical spill on Westmount Road, okay, at 7:30 this morning on your way to work, and this awful smell of hydrochloric acid, okay? What would you do? You would call the police. The police said, oh, we don't want to talk about it. It never happened. Go home, move along. What would you do? What would you do? We take a video. What would you do with the video? Post it somewhere, right? What allows you to post it and have the sense that other people can watch it and find it? It's a network, right? There's the underlying internet. You kind of assume that when you post it, right, it's going to be available. I could take a video in the 80s. I had a camcorder. I could take a video. It would be on something like a cassette, right? And then I'd stick it in my shelf at home, but nobody else could watch it but me, right? If I put it on the internet today, and it goes viral, it becomes publishable, suddenly everybody, right? If I put it up here, and I called the police, they said nobody wants to, we don't want to take action. It's going to be front page news tomorrow, right? It's going to spread. So that is citizen journalism, that's citizen activism. Why is that possible? Okay, why is it possible today? It's because we have the internet. Because we have a system that is quite remarkable. It's a system where you have more than 1 billion people, close to about 2 billion people, who have access to information, any information they want, anytime they want, and pretty much, on any device they want. You can go to it on your cell phone, on your iPad, on your tablet, even on your playbook, okay, on your desktop PC. You can get access to information, ideas, dissenting ideas from people you don't really want to hear about, or consenting ideas. You can build virtual communities. You can do all of this because of the internet, okay? And so what this course is about is to pop the hood of the car. Okay, there's the internet, kind of say, okay, what's going on under the covers? What makes it tick? What makes it possible for us to build a system that scales to 2 billion people, that supports free voice? Skype is free. How can you have free voice? Okay, 20 years ago, making a long distance call cost you $1, $2 a minute. Now it costs you $0, right? 20 years ago, your phone bill, monthly phone bill was, I don't know, $150. Now it's $5, $2, $0, right? 20 years ago, you could not imagine having a device you carry in your pocket which accesses Google, because Google didn't exist and the devices didn't exist. Cell phones were about the size of suitcases, and you would carry them in your suitcase. So these changes, these technologies, these principles which put together the internet is really what we're going to focus on today. And my belief is that it's going to change, has changed things already. It is going to continue to change things in a very dramatic way. So to understand this, there's this progression which are called atoms to bits. So atoms to bits basically says that any information that is represented in atoms is going to be put into bits. This is a statement from about 15 years ago, actually, by Nicholas Negroponte from MIT. And so let's take, atoms. Information as atoms. So what that means is, let's say I give you a bill, right? Somebody's going to send you a bill for your cable TV or phone or whatever it is. That's information presented as atoms. And what they want to do now is email you, okay, the bill. So the information content hasn't changed, but now it's coming to you in a way where the bits are being sent to you on a network. So in the 80s and the early 90s, all information was basically sent as atoms, okay? So if you wanted a book was a physical thing, right, that you'd go to the library for. If you wanted to read a paper, the same thing. So everything was atoms as atoms, which means you have to send it, okay? It's expensive to move it because you have to put it on a truck or a bus or a plane or a boat or something, and ship it. To the extent that these atoms are representing bits, we can move them on networks. Once you build a network, it's there. You can push anything you want through it, right? Just pushing bits out. So let's take an example of industry, the music industry. How was music done? So somebody would play a song, and then they would record it, and then the record would go on discs or CDs or cassettes or whatever, and then that would be shipped to warehouses, and you'd go to a music store and you'd buy these music. Or same thing for video cassettes, right? Blockbuster. Where is Blockbuster today? Where is Blockbuster today? Blockbuster today is disappeared, it's gone, it's evaporated. Okay, music, well, they're fighting very hard, but they're going to disappear too. Okay? Because whenever your business is built on atoms encoding information, somebody else is going to come along and say, we're just going to make it bits, and we're going to ship it on our network, and you're going to go away. That's happening to books, newspapers, music. It's happening to even things like consulting, right? Medical interpretation of CAT scans. Okay, because the atoms here are the technicians who are interpreting your scans. Why do you need to have the CAT scans being interpreted in London or Hamilton when you can have it done in China? Okay, there are cases where it's unbelievable, but it's actually true. When you pull into McDonald's in the US, in some parts of the US, you speak in the little speaker, right? And you say, I want to order a burger and fries. You know where that voice is going to? That voice is going to suburban housewives in Utah who are listening to it and typing up on a computer what the order is, and that order is going to the cook in the back of the McDonald's. Because then they don't need to have somebody listening to this being paid. You can pay somebody part-time wages, and in Utah they're sitting there, they have nothing to do, they're listening to orders and typing it up. Why is that possible? Because you have bits and you have the network. Okay. You don't have human beings as atoms, you have bits and networks. So this kind of outsourcing which you hear about, okay, you hear about industries being redone, transformed, changed, all that is happening because of the internet, because of networking. And that's why this material is important. Because this is, I used to say, it's $1 trillion change. That in '95 I was writing a textbook, and I said, computer networking is $1 trillion thing, and people were laughing, oh, you're kidding me. No, it's not $1 trillion, it's $100 trillion system. Everything is changing. It's changing under us. And what is going to happen in the end and what's going to happen before is going to be as monumental as the difference between copying out manuscripts with quill on parchment in the medieval abbeys versus, printing press. That change which happened between, 1420 and 1500, that change is going to happen between 1980 and, let's say, 2050. Okay, by 2050, the world will be completely different. Okay. And in ways that we don't know what it's going to look like. And hopefully this course is going to give you some idea of what we can do about it. What you can be as informed citizens, as informed scientists, whatever your career takes you, to understand what's going on with the network by engaging with it and going one level deep below it to see what's going on under the covers. Okay, so that's the purpose of this course. Okay, so we learn sort of the networking from the user's perspective. So you're all users of the internet, so you learn from the user's perspective what's going on. You learn about the principles. What does it take to build this, to put it together, and then the technologies. Okay, so we'll be focusing mostly on the principles. There'll be some technologies as well. You'll get hands-on use of the technologies. Okay, but it's big stuff, it's very important stuff, and now you know the reason why we're offering a computer networking course for non-majors, because this is really going to change everybody's lives. No matter what your major is, you're kind of affected one way or the other. Okay, so good. Let me move on. So I got lucky. I started working in this more or less by accident in 1988. And when I learned about this, I was like, wow, this is great. I was doing my PhD at the time, and I went to my professor and said, I want to work in this thing called computer networking. He said, oh, what's that? Never heard of it. And so for the first year, I didn't have an advisor because there was nobody in the faculty at Berkeley who understood networking. There was nobody doing research in networking. It's kind of fascinating to see, imagine that. But again, I got lucky with that. Okay, so we're going to study the internet. All right, that's the most important computer network today. And one could argue cell phone networks are more important, but cell phone networks, by and large, today have become merged with the internet in many ways. So we will talk about cell phone networks, how cell phone networks operate in some detail. So you'll understand exactly what happens with your phone. But then we'll talk in the context of the internet. All right, so I should remember to tell you one more thing before I forget. Okay, so what is the internet? So what do you think the internet is? Anybody have any suggestions? No, it's not a trick question. The first one, the triangle, is a trick question. This is not a trick question. I just want to know, what do you think is the internet? Information moving through a network, okay. Internet. Okay, so information moving through a network is the internet. Isn't that kind of recursive? I mean, the internet is the internetwork, right? So you kind of define the internetwork in terms of the network itself, so that's not particularly helpful. So maybe you want to refine that? What would you say? You don't know, okay. Yeah? A bunch of servers, okay. So what about your browser? Is that part of the internet?
Yeah, but you're accessing information.
No, you said the internet is a bunch of servers. I'm writing down what you said. I didn't make it up. So is your browser part of the internet?
What makes up the core? That's where all the...
I didn't say the core. I just said, what's the internet? I just said, what's...
This is a trick question.
No, not at all, not at all. I'm trying to plumb the depths of your ignorance. I want to know how little you know. No, but by the end of this course, you'll know, actually in about 10 minutes, you'll know a lot more than you about the answer is. Yes?
I think it's an interrelated network connects people or maybe objects that can pass through information.
Interrelated network that what does what?
That
connects people.
Objects.
Connects objects.
Not necessarily people.
Objects.
And pass through information.
Not just people. Okay. and passes information, you said? And passes information. So how many people think that's the real definition? Interrelated, what does it mean by interrelated networks?
I mean, like I can pass information to you and you can
Yeah.
pass to me.
So interconnected, connected. Okay, that's good. All right. Network that connects objects, not just people, and passes information. That's getting close. That's getting close. Anybody else want to refine this? Yes? A collection of smaller networks. Oh, great. And when do you bottom out on this, by the way? What is a network? There's this story about somebody was a professor of physics, and he's giving a lecture, and at the end, any questions, and his little notes, he says, I think the earth is on turtles, standing on turtles. He said, really? And what's a turtle standing on? He says, another turtle. Where's that standing on? He says, don't worry, young man, it's turtles all the way down. So it's a collection of smaller networks all the way down. This is too recursive for my taste. I mean, where do you stop? Collection of smaller networks. And that's a collection of smaller networks down, all the way down, like turtles, all the way down? Down to the user. to the user. And no servers. What happened to servers? She said it's all servers. Okay, anybody else? Okay, so, there's a story about the 7 wise men or 7 blind men and the elephant, and each person sees the elephant as being a different thing. And that's also true of the internet. And so there are at least 2 different ways of thinking about the internet, and explain what it is. What we call the service view. Actually, I can give you 3. The service view, the topology, or the... Then I could probably say another view is sort of the formal... I'll tell you the formal definition as well. So let's think about these 3 things. So the service view of the internet says, what does it give me? Okay. So suppose I ask you to define the post office, right? Everybody, well, not everybody knows what the post office is. Let me see. I had a different example over here. Yeah, I guess post office. Yeah. So if you go to a post office, most of you have used the post office. Has everybody used the post office once in their life? Okay. Good. So if I say, what's a post office? You can say it's a service that delivers letters and parcels, right? Anywhere in the world. And that's a pretty reasonable definition of the post office, okay? It's a thing that delivers letters and parcels, okay? And that's what we call the service view of the postal network. It doesn't say how it works, right? It doesn't talk about servers, doesn't talk about post boxes or, anything like that. It just says, this is what it gives me, right? And so the internet, from the service view, is something that delivers bits from one end to the other, anywhere in the world. That's it. Okay? So it's a bit delivery service. You can send bits out, or you can receive bits, and from somebody else also on the internet. So that would be, you can think of the internet as being sort of a bit exchange service, right? And that's the service view. Okay? And as you can see, it sort of encompasses what was said here, information moving through a network. Yeah, so we view bits. I assume you all know what a bit is. The bit is the smallest amount of information corresponding to 0 or a 1. And so we can think of information moving through a network. It's sort of right. The service view is, in fact, saying that it's bits being delivered to you. And this one is interrelated network that connects objects. You're probably talking about connecting objects because exchanging information, right? The connection is through the exchange of information, which is also the service view. And collection of smaller networks, well, these 2 guys are actually related to the topology view. The topology view is how do we build it as a service? And I'll come to that in just a moment. Let me just talk about the formal definition first because that's kind of important. So how many of you have heard the term IP address? Okay, IP address? Okay. So actually, let me turn it around. How many of you have not heard of the term IP address? Could you please raise your hand? Okay, so everybody has heard of the term IP address because one way or the other, if you use the internet, it kind of shows up one time or the other. Now, you learn about IP addresses in very great detail, but the formal definition of the internet is basically the set of all reachable IP addresses. So if I can get from one IP address, where IP stands for Internet Protocol, that's a protocol I use to talk to other internet-connected hosts or computers, I can get to any other IP address, I will say they're part of the internet, okay? And so it's kind of funny because from my home IP address, I can certainly get to Google, but I can't get to your home IP address because you're behind a firewall, right? So from my perspective, my view of the internet is different from your view of the internet because my view of the internet includes a lot of servers and things like that, but not you. And similarly, your view, okay? So the set of all reachable IP addresses means that there is no one internet, okay? There's no one internet. Even formally speaking, everybody has a view of the internet from the point of attachment, okay? And so this is a view as I see from here. It's a very relativistic view of the world, but that is the internet because if you can't reach somebody, as far as you're concerned, they don't even exist, okay? To first approximation. Okay. Now, of course, what they do can hurt you, but as far as you can't reach it, yeah.
So every computer has its own personal internet?
Every computer has its own view of the internet. the view of the internet. So there is a sort of it's like saying if I don't know it exists, how can I say it's part of the internet, right? It's not really existing in some sense, right? It's beyond the event horizon, so to speak. But at least we have a good set of, so I can say, okay, from this point, all the IP addresses that can be reached, this constitutes the internet. That's a pretty good, reasonable definition. Now, it doesn't say anything about the topology. It doesn't say anything about the service. It's just telling you reachability. Okay, it doesn't say, yeah, I can get the web on it, I can get Skype on it, I can get this and that and the other. That's the service view. Okay, right? But this is the okay. Any questions about that? So we'll kind of focus on this view for the most part. So we'll start out the course. Just today I'll talk about topology. Next 20 minutes we'll learn a lot about topology. And then the next three lectures will be on service view, the application layer as we call it. And we'll learn about the applications. And then we'll do more about the topologies under that later on. Okay, I want to now talk about one last thing before I get into topology, and that is what is a protocol, because that's a word we'll use a lot. So to take off this, what I hear by services, so the basic service of the internet is bit transport. I give you a bit, move it to the other end, so I tell you destination where to go to. So it says go to postal service, say here's an envelope, that's the address. Move the contents over. In the internet, we say, here's a packet, it's a collection of bits. Here's the header, here's the address, go send it, and it goes there. That's the basic service of the internet. It's a way to move packets with some destination address. Okay, that's it. Well, we talk a lot about protocols, so, okay, I'm not going to ask you what a protocol is because it's a bit more complicated. You probably heard the word protocol in the word IP, Internet Protocol, or you heard a protocol when the Queen visits, so the protocol is that this person should be addressed in this way and that person should be talking this way, etc. Protocol is a way to formalize it's a formalized relationship. And interaction. So, for example, you have a browser and you want to go to Google and you want to say, search for this term. So you have to tell the server something, right? You can't just throw random bits at it. You got to say, okay, I want to search for this term and this term, but not the other term, whatever. There's some specification. That's the protocol, okay? So, in order to be part of the internet, every element of the internet needs to obey some set of protocols. Okay, and these are not, these are artificially designed. People design these protocols. The internet designers sat down and said, "This is the way we design the protocols, and if you obey these protocols, what will happen is the other person will respond." Okay, so imagine that you're in a foreign country, some country where you don't speak the language, and you're asking for directions to go somewhere. Okay. How do you do it, right? Let's say, I'll pick I don't know which country to pick where nobody here knows the language. Let's just pick, you go to Mars, right? And you ask the Martians, which way is it to the grocery store? What do you do, right? It's difficult. If you go to the Martian and you say, which way to the grocery store in English, in Martian language, it might be a very bad, vulgar insult, and they might shoot you with their death ray, right away. Right? It's not a good idea. So unless you have the protocol, you're kind of unable to communicate, right? You can see that the protocol and communication go together. And so what we do is that as engineers, as internet designers, we specify in great detail what the protocol is going to be. So I'm going to tell you this, you're going to tell me that. If you don't tell me that, I'm going to do this instead. And if you don't tell me that soon enough, I'm going to do something else. I'm going to try again. I'm going to try 3 times. After 3 times, I'm going to stop, right? So those are the kinds of things that we decide, and this is the internet protocol. We'll study those in some detail. For example, what is the web protocol? What is the email? How do you send email? The email protocol. What is the protocol used by BitTorrent clients in order to communicate with other people and get BitTorrent content? What is used by Skype? right? To say, okay, I want to make a phone call to this Skype address. What is this protocol used by the name service, name resolution? So we'll study those kind of protocols. Okay, so that brings me to this kind of topology which I'm going to discuss now, which is how do we, okay, I think the board is big enough. Okay, so how do we put this whole thing together? So again, remember, this is a third view of the internet. One was this formal definition, IP addresses that are reachable from each other. The second one was it provides me the service of packet transport, bit transport. But now I'm going to talk a little bit about how the whole thing kind of wires together, and some of you may be familiar with this, but I will go through it anyway. So at the end, everything is made up of links and routers. Okay, you can think of it in links and nodes. So what is a link? So if I go here and I pull out this thing over here, this blue cable over here, is probably familiar to most of you. It's called a Cat5 cable, category 5 cable that represents kind of what it is. And on the end, this little thing, this plastic thingy, it's called a RJ45 connector. RJ45 is the name of the standard that connects it. So this Cat5 cable and RJ45 connector, or a wireless hub, I'm looking for one, I don't see one here, maybe in the hallway. These are the places where you get access to the internet, right? You have a Wi-Fi hub or a RJ45 connector. And what we have is we have endpoints, which could be your cell phone, or it could be a desktop computer, okay, or whatever else. You have your toaster, okay. Let me see, my toasters, yeah, it looks sort of like a toaster there. These guys are connected either on a wired or a wireless link, and they always end up to sort of your internet access point. So the access point, or AP, is what we use for Wi-Fi. Okay, and then your cell phone also connects to a cell tower. These cell towers are actually easy to spot. They're towers which have a triangle on top, like a triangular platform with these vertical antennas about this big. So if any time you're going along the 401, or even if you go along Westmont, you'll see towers with a triangular platform and 3 of these things. That's a cell phone tower. Okay, there's actually 6 within sight of campus. And so you can do Wi-Fi or cell. So these are the ways to get from the end device, end system. And we also use the word commonly, it's called host. That's sort of a, end host is a, I don't know, jargon in the internet, end system or a host. And this is what we would call the access link. This connection is the access link. Okay, so this is the way to get from the end system to your first point of attachment, okay? And typically it's either wireless or it's wired, okay? After this, okay, we're getting into the core of the internet, right? So how does it work? So let's think about that. The blue wire, where it's going is that it goes through one of these pipes, I guess. It should be one of these pipes right here. Huh. I don't know where it goes. Okay, so maybe they go under the floor. But there's a wiring closet at the end of the hall. Okay, and a wiring closet, if you open it up, it's just what it says. It's a closet about this wide. You open it up, and it's got a rack, okay, like a shelf. Lots of wires coming out, one from each classroom, and from the Wi-Fi access points as well. So the Wi-Fi access points. So you have a closet, the wiring closet. And the wiring closet has got this is the Wi-Fi access point, and these are the wired stuff. So these wires will actually go into the wiring closet like this. Okay, so the Wi-Fi access point goes to the internet access point. This one goes into the wiring closet, and it goes into what's called a switch or a hub. And so it's a bunch of wires coming in, right? What we're going to do in the bunch of wires is we're going to put them into the switch, because this switch or hub, which is where all these wires are coming, and there's typically about, each switch or hub will take 24, 48, something like that. That's a usual number. Let's say 24 to 48 things. And it'll have one output link going out, okay? And so we're taking a lot of wires and putting in one the way it works is that this one is much faster than the input one. So each of these guys will be at a particular speed, but this is going to be much faster. Okay, and I'll talk about speed, what that means later, but just go with the picture right now. So that's this wire coming out. Now, a question about this? Yeah, okay, so each of these wiring closets has a bunch of these hubs coming out. Wires coming out, and these wires, which are all coming from different floors of MC and from DC and other places, actually, but just to focus on MC right now, they're all going to go into what's called a router. And the router for MC is in the basement of this building. So there's a building, and we have about, I don't know, probably about 2,000 or 3,000 access points, and wired offices and Wi-Fi access points. So all of those 2,000 or 3,000 endpoints are going to go into one router in the basement. Okay? The same thing is done at every building on campus. Every building on campus has got the same kind of wires going through, access points, going to these switches or hubs, going to routers, okay? And they're all going to typically in some room in the basement. Now these routers are now interconnected to sort of a big router. I'll just call it a big router. And this big router is the campus router. Actually, there's two of them. And they happen to be in the basement of MC as well, but they could be anywhere, right? The IST runs them, and they're kept in this basement over here. And so we have wires coming from each building, and it go into this big router over here, etc. And there's about, I don't know, about 25 or so big routers. And you'll notice that at each time we aggregate stuff, put stuff together, it's about 25 to 100. Okay, so about 25 wires coming into a switch, about 25 switches going to a router, about 25 routers going to a big router. This big router is now got all the traffic into and out of University of Waterloo. All of that goes on that router, and obviously we don't want that single point to fail. So the way we implement it is actually we have two big routers, one behind the other, and if one fails, the other one takes over, but that's a detail. Conceptually, it's only one big router. Now what this router is going to do, it's going to talk to the rest of the internet, and what that looks like is something like this. We have this notion of what's called the ISP, Internet Service Provider, and the Internet Service Provider is something that is basically a connection of routers. Okay, they have routers connected in some kind of graph, and the graph is some arbitrary connection. Okay, but the important point is that they provide service to different universities. So here's Wilfrid Laurier with this own kind of wiring over here, and that ISP could be, is connected to here. So we actually have three ISPs providing service to University of Waterloo. Okay, we don't want any one of them fails, it's still okay. So we have one is called Orion, which is a Ontario Research Network. There's Cogent, and then we also have Hydro One, which is actually the hydro company, but it also provides internet service, because if you have a lot of land along a strip, where you can put electrical cables, you can also put in fiber optic cables, and so you can get internet service when you have electricity service. So Hydro One provides our internet service as well. Anyway, so they have three ISPs. So this router is connecting to actually three ISPs, like so. These ISPs are all in Ontario, right? But Cogent actually is all over North America, but Hydro One and Orion is certainly only in Ontario. So how do we get somewhere else? So these ISPs over here are called Tier 2 ISPs, and they actually have links to Tier 1 ISPs. Okay. The Tier 1 ISPs, and there's about 25 of them. Everything is 25. So about 25 of them in the world. The Tier 1 ISPs are global, okay, for the most part. Okay, some of them are not, but most part they're global. So for example, Cogent has links to, it has presence in Europe, different parts of Europe. Deutsche Telekom has presence in North America and Europe. AT&T has presence all over the world. cable and wireless. So these are all tier 1 ISPs. You don't really hear much about them, okay, because these are, sort of in the guts of the network. You don't really talk much about them. But the tier 1 ISPs around the world talk to each other, and what they actually do is, I should be more precise over here, is that they actually have these long distance links like this that form this network like this, okay. These links now are very long, okay. For example, Cogent, which is our ISP over here, let's say this one is Cogent, has a link from Denver to the UK, to London. Okay, this is Denver, and this is London, and so we have a Denver to London link, one hop, right? So you go to Denver to their back office, you open up the room, and there's a wire going out through the wall, and that wire is going all the way to London, just all the way over, okay? That's the Denver to London link. Similarly, there are links from London actually to the rest of the world. There are very long fiber optic cables. If you ever want to look it up, you can look at this thing called FLAG, fiber link around the globe. And fiber link around the globe is exactly what you'd expect. There are these links which go around the globe. You have these ships, and on the ships they have big spools of fiber optic cables which are encased in steel. Okay, why are they encased in steel? Anybody know? Because otherwise they get bitten by sharks. The sharks actually bite right through the cables. So these are steel jacketed, heavy cables. They put steel, and then they put tar, and they put some more steel, and then they lower it to the bottom of the Atlantic and the Pacific, and they go to these very long links. So in the US, for example, you have links going to Hawaii, Hawaii to Japan, Japan, Singapore, Hong Kong, you name it. And then what happens is the exact same thing happens on the other side. Okay, we have the tier 1 ISPs talking to tier 2 ISPs, talking to what are called campus networks. This is a campus network talking to routers, talking to switches and hubs, talking to this. Okay, and so if you're going to send, let's say you want to do BitTorrent, and you have somebody who's has a bit of a file, and that file is somewhere, let's say, for the sake of argument, in California, and you want to exchange an IP packet and say, give me that bit of that movie, that I'm downloading illegally, right? So your packet is going to go from your Wi-Fi access point to your switch, which is actually most likely the DSL or cable modem, right? The cable modem is going to talk to a router. This router is actually at Rogers, or who your DSL or cable modem provider is, and that goes into their big router, Rogers, and that goes into their ISP, goes into the tier 1 ISP, right? It's going to go to, let's say, Denver. From Denver, it's going to make a hop to California, and California it goes back, and then all the way back to that person over there, and they give you the packet, and then all the way around. This is the topology of the internet. And the one thing I did not mention, which is rather significant, and luckily we have a few minutes, so I'm going to talk about that, is that not everything in the internet is sort of at the end host level, right? Somebody said bunch of servers. You said a bunch of servers. In fact, a lot of our services today come from a bunch of servers. So where are these servers? Well, these servers are actually in things called data centers. And these data centers can be viewed as being equivalent of a tier 2 ISP, okay? So the tier 1 ISP, okay, will have this special kind of heavy duty, high bandwidth link into a warehouse, okay? And the warehouse will be is packed, ceiling to floor, wall to wall, with two things: computers and cooling equipment, okay? Air conditioners. Because the computers are creating a lot of heat, and you need to get the heat out, right? So for every watt that you spend on computing, watt of energy, I should say watt of power, you're going to spend 1 watt of power on cooling, okay, typically. That's why the data centers are built either in Siberia, where you can open the windows and cool it, or in northern Ontario, I guess, would be a equally good place, or they're built next to power plants, in the Columbia River Gorge, or next to coal-fired power plants in Virginia, because you can get electricity cheap. The electricity is used to cool the servers. So anyway, so imagine, you've seen a Mac Mini, right? So it's about this big. right? So imagine I had a lot of Mac Minis. I could, if I just tile this over here, I guess I could fit, I don't know, let's say I could put about 50 legs there and 100 this way, so I can get 5,000, right? And if I stack it up 20 high, that's 100,000, okay? So I could put 100,000 Mac Minis in this space, okay? It would be very hot, and it would all melt after an hour or so. But if if cooling was not a problem, I could fit 100,000 in this space. And so it's not surprising to know that Google fits 1 million servers in the data centers, okay? So it's 10 rooms like this. You could fit 1 million Mac Minis in here. And what Google does is they design their own processors, they design their own own servers, they design their own networks, and they put in these data centers, and they piled up. And these provide a lot of the services you expect from the internet today. They provide your email, they provide your search, they provide storage, they provide Netflix, YouTube. They all come from data centers. So we'll spend some amount of time talking about how data centers work, because they're really pretty important. So how does that work? Let's say I want to do a search on google.ca. Google.ca happens to be, the Canadian version of Google happens to be in Toronto. So that would actually be coming through Cogent. So Cogent actually has a link here as well. As you can imagine, these data centers are connected multiply to make sure that they're accessible. So when you send a packet to Google from, let's say, your cell phone, it's going to a cell tower. And from here, it's going to go into a similar switch or a hub, okay, into a router, into the campus router. But if you, let's not do the cell phone, let's do it from the Wi-Fi. It's going to Wi-Fi into your hub, to a campus router. That's going to go to Cogent. Cogent sends it to Google. Google gets the query. Inside, they have a very complicated network, which Andy will discuss. That's what he studies. And it'll get to one of the servers over there, and then it sends its reply back. Now, the beautiful thing is you can actually trace this out. There is a tool. And for your first homework assignment, you'll actually find out exactly where the Google data centers are. You'll find out what path it took. You'll find out how long it takes, and how often the path changes just by observing. So you actually find this exact topology by looking at it. So I'm going to give you one last bit of jargon, and then we'll stop. So each of these things over here is a collection of routers, is actually owned by a different entity. Okay, it's not like who owns the internet? Well, nobody owns the internet, right? It's like saying who owns the global road network? Well, nobody does. Okay, each piece is connected, but each piece is owned separately, right? The driveway in your house is not owned by, World Roadways Corporation. It's your driveway. In the same way, nobody owns the internet. So each of these is autonomous, is what we call it. And we call this, each little piece, an autonomous system. And we abbreviate it as AS. And so what we have is that each autonomous system has its number. It's a kind of a unique directory of numbers. We give a number. So we can actually find the AS for so Waterloo, this whole thing is one autonomous system, and this another autonomous system, etc. And so the internet can then be viewed as a collection of smaller autonomous systems. So you said it's a collection of smaller networks? Yes. It's a collection of smaller autonomous systems, where internally they are made of switches and routers and links. All right, so we'll stop with that, and next class we will continue with application layer protocols.